Welcome to our Quantum Deep Dive, an explainer where we break down big ideas. Today, we're digging into an incredible essay by Georg Ove Schneeppat about one of the most important discoveries in all of science, Planck's radiation law. It's a story about how one stubborn, nagging problem forced a physicist to basically question the very fabric of reality itself.
Okay, so let's set the scene. It's the late 19th century, and physicists, they thought they were on the verge of knowing pretty much everything. Seriously, they had Newton's laws for how things move, Maxwell's equations for light. The universe seemed like this big, predictable, well-oiled machine. But one seemingly simple problem was about to come along and shatter their entire worldview.
And that problem was all about something called blackbody radiation. Now I know, that sounds super technical and complicated, but the basic idea is actually something you see all the time.
Just imagine a perfect black box, an object that soaks up every single bit of light that hits it. Now, what happens when you heat that box up? It starts to glow, right? First a deep red, then orange, then bright white hot. Physicists wanted a single, beautiful law that could predict the exact color and brightness of that glow at any temperature. You'd think that'd be pretty straightforward.
So, using all the trusted rules of classical physics, a couple of scientists came up with something called the Rayleigh-Jeans law. And for part of the puzzle, it worked great. It made spot-on predictions for long wavelengths of light, stuff like red light and infrared. It really looked like they were cracking the code.
But, and this is a huge but, when they looked at shorter wavelengths, like ultraviolet light, the law didn't just fail, it failed spectacularly. In the real world, the energy peaks and then drops off. But the classical prediction? It went completely nuts, suggesting that the energy should just keep climbing and climbing all the way to infinity. Which is, absurd.
This wasn't just some minor rounding error. This was a deep, fundamental break in their understanding of the universe. It was so bad, it got this incredibly dramatic nickname, the ultraviolet catastrophe. It was a clear, flashing sign that the laws of physics, as everyone knew them, were just wrong.
And this is where Max Planck enters the story. He was a German physicist, and this problem really bothered him. Now, what's so interesting is that Planck was no revolutionary. He was a conservative thinker who loved the established laws of thermodynamics. His whole goal was to save classical physics, not to tear it down.
So, after years of hitting a brick wall, he tried something he didn't even want to believe. It was a mathematical trick, a move he later called an act of desperation. And it just goes to show you, sometimes the biggest discoveries happen when you're forced to consider ideas that seem completely crazy.
And here it is, the crazy idea. For centuries, everyone assumed energy was continuous. Think of it like water flowing smoothly down a ramp. Planck proposed the exact opposite. He said, what if energy is more like climbing a staircase? It comes in little individual packets. You can be on one step or the next step up, but you can never, ever be in between the steps. He called these little energy packets quanta.
And he even came up with this simple but world-changing equation for it, E equals h nu. It just says that the energy of one of these packets is tied to its frequency. And to make the whole thing work, he had to invent a brand new number, a new constant of nature, which he called h.
So, armed with this totally radical new assumption, this idea that energy comes in steps, Planck went back to the drawing board. And in the year 1900, he cooked up a brand new formula, one that would change physics forever.
And this is it, the famous Planck's radiation law. The amazing thing? It worked. It worked perfectly. It wasn't a partial fix. It matched the real-world data across the entire spectrum, from the long wavelengths to the short ones. The ultraviolet catastrophe was completely, totally solved.
And at the absolute heart of it all was that little number he invented, the Planck constant. H. I mean, look at how tiny it is. That's why in our big, everyday world, we never notice energy coming in steps. The steps are just too small to see. But this number is profoundly important. It sets the fundamental granularity of our universe. It's the size of the steps on that cosmic staircase.
So, how did this fix the problem? Well, think of it this way. To make a packet of high-frequency light, like ultraviolet, the system has to pay a really high energy price. It needs one big, chunky quantum of energy. And it's just a lot harder for the system to make those huge energy leaps than it is to make lots of little ones. Because those big energy packets are just too expensive to produce easily, the glow naturally fades out at high frequencies. The catastrophe was gone. Now, Planck honestly thought he just found a clever math trick to solve one annoying problem. He had absolutely no idea he had just accidentally kicked open the door to a bizarre new reality.
His idea didn't just sit there, it spread like wildfire. Just 5 years later, a young Albert Einstein ran with it, saying light itself must be made of these quanta, what we now call photons. Then Niels Bohr used it to figure out why atoms are stable, and before long, physicists like Heisenberg and Schrödinger built the whole amazing, weird, and wonderful field of quantum mechanics right on top of Planck's foundation.
This was way more than just new physics. It was a whole new philosophy. The old clockwork universe of Isaac Newton, where if you knew everything now, you could predict the future perfectly, that was over. It was replaced by a strange new reality, governed by pure chance, probability, and a fundamental uncertainty about what we can ever truly know.
Okay, so why are we talking about a discovery from over 100 years ago? Why does this matter to you? Well, because Planck's law and the quantum revolution it kicked off is literally built into almost every single piece of technology that makes our modern world run.
From understanding the afterglow of the Big Bang, which is a perfect blackbody radiator, by the way, to the semiconductors and LEDs inside the very device you're watching this on, it all goes back to Planck's reluctant little idea. Lasers, quantum computing, medical imaging, you name it, its roots are right here.
So if there's one thing to take away from all this, it's that Planck's discovery wasn't just some new equation. It was a profound realization about what reality is. He showed us that at the tiniest, most fundamental level, the universe isn't smooth and continuous. It's grainy, it's pixelated, it's quantum.
And that leaves us with one last big question to chew on. A major crisis in physics, a catastrophe, led to its single greatest revolution. Right now, physicists are staring at their own weird anomalies, things like dark matter and dark energy. What if those are our modern ultraviolet catastrophes, just waiting for the next Max Planck to have another desperate idea? That's all for this explainer, which was based on the fantastic essay by York Oa Schneppe. For more deep dives like this, you can check out schneppe.de. Thanks for watching, and goodbye.
Schneppe.de is a private project by Jörg Oa Schneppe dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.